Fluid mechanics. Behavior.
The experiment demonstrates laminar, transitional, and turbulent flow using the Osborne Reynolds apparatus. The water flows from a header tank through a transparent pipe, allowing flow patterns to be visualized using dye injection. The flow rate is controlled and measured, enabling the calculation of fluid velocity and the Reynolds number. The Reynolds number is dimensionless parameter used to classify flow behavior. Laminar flow is smooth and transitional flow is mixed and turbulent flow is chaotic. It depends on the velocity, pipe diameter and fluid viscosity, and it's independent of pressure. This experiment helps relate fluid flow behavior of the real industrial chemical process. The main three objective of this experiment is to study fluid flow behavior in a chemical process, to calculate the Reynolds number, and to identify the laminar, transitional, and turbulent flow conditions.
So here I will explain the procedure, which is it have 4 parts. The first thing is the initial setup. So the water in the above V1 was opened and the water was allowed to enter the settling tank, and a small overflow spillage was ensured through the overflow tube to maintain a constant water level, and the water was allowed to settle for a few minutes before the experiment begins. Okay, for second part is dye injection. So as we can see, the Osborne Reynolds at the uppers, we can see it have a dye injector. It was a lower until it was visible inside the glass observation tube, and then the dye control valve 4 was slowly adjusted until a steady flow of dye injection was achieved. Secondly, is laminar flow. So here we can see the laminar flow, or the laminar design was occur, which is the inlet above V1 and the outlets above V2 was regulated until a strict identifiable dye line was achieved. And then this indicate laminar flow where the calculated Reynolds number was less than 2100. So the flow rate at the outlet above V2 was measured using a volumetric method. And then the last part is transitional and turbulent flow, which is the valve where readjusted to increase the water velocity until the dye began to mix or become unstable. And then the transitional flow was observed when the dye started to fluctuate, occurring at Reynolds number between 2100 and 4000. And then turbulent flow was reached when the dye dispersed and mixed completely with the water, occurring at the Reynolds number above 4000.
I will explain how we process our raw data to identify the fluid behavior observed in Osborne Reynolds apparatus. Our primary goal was to compute the Reynolds number, a dimensionless parameter used to distinguish between laminar, transitional, and turbulent flow. To find the Reynolds numbers, we first determine the flow rate by measuring the volume of water collected over 60 seconds. We then apply the formula RE equal to Q times D over A times V. For this calculation, we use the fixed glass tube diameter of 0.0156 meters and area of 1.91 exponent -4 meters square, and the kinematic viscosity of water at 25 degrees Celsius, which is 0.89 exponent 6 meter square per second. Looking at our result, we categorize the flow into 3 distinct regimes based on theoretical threshold. For laminar flow, we recorded Reynolds number were approximate 114, which is well below 2100 limits. For transitional flow, as we increase the flow rate to roughly 2.8 exponent -5 meter cube per second, our Reynolds number jumped to the 2050 to 2631 range, fit perfectly within the 2100 to 4000 transition zone. Finally, for turbulent flow, our rate reached about 4.8 exponent -5 meter cube per second, resulting in Renault number exceeding 4,300, confirming turbulence as they surpass the 4,000 threshold. This calculation successfully validated our observations. As the velocity and flow rate increased, the Renault number rose, causing the fluid to shift from steady streamline to fully mixed turbulent state.
Imagine injecting a thin line of dye into a flowing liquid at low speed. It stays as a smooth, straight line, but as the flow increases, it starts to wiggle and suddenly bursts into mixing. This is exactly what the Osborne-Reynolds experiments demonstrate using the Reynolds number. Based on the results, laminar flow had Reynolds number below 2000, showing smooth and orderly motion. The transition flow ranged around 2590 and turbulent flow above 4,400. However, in real industry situations, flow behavior more complex due to factors such as pipe roughness, fittings, and fluid properties. In fluid mechanics, we have three types of flow, which are laminar, transition, and turbulent. Laminar flow is smooth and orderly, like honey flowing leaves. Transition flow is an intermediate stage where the flow starts to become unstable, while turbulent flow fast and mixed, like fast-moving river water. These flows are applied differently based on the process needs. Laminar used where smooth control flow required, such as transport viscous fluids. Turbulent flow used because it enhances mixing, heat transfer, and mass transfer, like in reactors. Transition flow is usually avoided in industry because it is unstable and difficult to control. This fluid mechanics experiment can be related to the top-heat paradigm. First is efficient resources management. In the experiment, we use water, time, and equipment carefully to obtain accurate results for laminar, turbulent, and transition. This reflects how chemical industry must manage resources efficiently in industry, ensuring minimum waste and maximum performance, like pipelines and reactors. Second is tolerance and teamwork. During the experiment, each group member had different roles, such as measuring flow rate, observing and recording data, and handle Osborne equipment. We had to cooperate, share responsibilities each other, and this builds tolerance and teamwork skills, which are very important in industrial environments where chemical industry must work together to solve fluid flow and process problems. Third is responsibility. We must handle apparatus properly, ensure safety, and take accurate readings without any errors. This reflects responsibility in both academic and industrial settings, where correct data and safe operation are essential to avoid accidents and ensure reliable processes. Fluid mechanics is very important in chemical industry because most industrial processes involve liquid and gases. It helps us understand how fluids flow, which is essential for designing pipeline and selected pumps to transport chemical efficiently. In industry, fluid mechanics used in equipment like reactors improves reaction rate and product yield. It is also important in separation processes such as distillation and filtration, where it ensures for better separation efficiency.
Renault number is important because it helps us identify the type of fluid flow, whether it is laminar, transitional, or turbulent. By knowing the flow type, we can predict how the fluid behaves, such as mixing, energy loss, and pressure drop in pipes. This is very useful in engineering applications to design efficient systems. The dye is used as a visual indicator of the flow pattern inside the tube. It helps us clearly distinguish between different flow regimes. For example, in laminar flow, the dye flows in a straight line. In transitional flow, it starts to fluctuate, and in turbulent flow, it mixes completely with the water. In industry applications, different methods are used to determine flow type. Flow meters such as ultrasonic or electromagnetic devices are used to measure velocity and calculate Reynolds number. Particle image velocimetry or PIV is used to visualize flow patterns. Pressure drop measurements across pipes can also help identify the flow regime. Additionally, computational fluid dynamics or CFD simulations are used to model and predict fluid behavior.
So for the conclusion, this experiment was successfully carried out to observe fluid flow behavior and determine Reynolds number for different flow conditions. The Reynolds number for laminar flow was 112.1645, which is below 2100, indicating smooth and orderly fluid motion. The transitional flow recorded a Reynolds number of 2589.967, which fall within the range of 2100 to 4000, showing an unstable flow characteristic between laminar and turbulent conditions. The turbulent flow had a Reynolds number of 4404.965, exceeding 4000, indicating chaotic fluid motion within significant mixing. Overall, the experiment results agree with fluid mechanics theories, providing that Reynolds number is an important parameter for classifying flow behavior in pipes, and it is widely applicable in industrial fluid transport and chemical processing systems.